We're discussing superspace and superfields, and this is something that you've heard about now in two sets of lectures by Mukund and by myself. So again, this is a topic that is well worth learning. So remember that superspace was the result of extending ordinary four-dimensional spacetime, and for today will only be in 4 dimensions, extending four-dimensional spacetime by adding an additional spinor Grassmann coordinate theta and its complex conjugate. And the superfield was a function x of theta, a function of x, theta, and theta bar, whose supersymmetry transformation properties were dictated by the following commutator. The commutator of S with the operatorial supercharges, which I denote by ordinary Q and ordinary Q bar, are given by acting on S with the superspace differential operators boldface Q and boldface Q bar, which I've written over here for your, to remind you what they look like. So this is an implementation of the supersymmetry algebra via differential operators. So essentially by translations in superspace. Okay, so that was the definition of a superfield, a general superfield. Any object that satisfies this, we call a superfield. And this thing on the right-hand side here, this differential operator expression acting on S, I'll also call it delta zeta of S. That's the SUSY variation parameterized by zeta. Very good. And we showed a bunch of different things. But one thing that will be useful today is the statement that if S is in superfield, then the supercovariant derivatives of S are also superfields. And then using, for instance, this anti-commutator, it also follows that an ordinary derivative of S. These are all superfields. Okay, and similarly, products of superfields are again superfields. So the last thing we discussed was that expanding x and theta bar components gives you the component fields, the ordinary component fields that are part of the superfield. So for example, you can start with some bottom component C of x and then some spinors and so forth until you get to the very top. And at the very top, you'll have things with 3 thetas times more spinors. Let me call them lambda and rho bar. And then the very top component, the theta squared, theta bar squared component, I call d of x. So that's the d term. D term is by definition just the top component of a long superfield. And the reason that we're doing all of this is because we would like to construct supersymmetric Lagrangians. So we would like to write some action. I'll write the action as I rather than S because I'm already using S for superfields. We'd like to write some action as the integral over spacetime of some Lagrangian density L of x. And we would like this action to be invariant under the Q's and the Q bars. So naively, you might think that what you should do is pick a Lagrangian that is invariant under the action of Q's and Q bars. So you might want to impose Q of L is 0 and Q bar of L is 0. But that doesn't work because using the anti-commutator of Q and Q bar, the charges Q and Q bar, right, using the supersymmetry algebra, you'll get the momentum generator, and the momentum generator commuted with L of x gives you a derivative. So this would imply that L is in fact constant. It's a trivial operator. The only operator that satisfies this is the identity operator. So you can't construct any interesting Lagrangians this way. So you have to do something a little more general, but that's fine. I mean, you know, this shouldn't surprise you too much. This also doesn't work, for example, if you try to demand that L is invariant under translations, right? If you know, the reason the action is invariant under translations is not because L is invariant under translations is because L transforms into a total derivative, which is then made translationally invariant by integrating over spacetime. So we're going to demand the same thing here. We're going to try to find Lagrangians, L of x, that transform into total derivatives under the action of the q's and the q bars. So a natural candidate for such an action is just the d term, d of x of this superfield, right? Because remember the rule for computing the supersymmetry variation of the component fields. What you do is you apply this formula to the whole superfield and then compare left-hand sides and right-hand sides. Well, if you want to compute the supersymmetry variation of d of x, you have to look at the theta squared, theta bar squared component of this formula, right? So on the left-hand side here, you would have q acting on d squared and q bar acting on d squared multiplied by theta squared, theta bar squared. So roughly speaking, you'll get an expression like this. Okay. So that's what you would like to match to a corresponding term on the right-hand side here. The q's and q bars differential operators consist of two parts. There's a part that has dd alpha and dd alpha bar derivatives. And that part will always reduce the number of thetas or theta bars. So there's no way it can produce a term with a theta squared and a theta bar squared. So that part of the q variation doesn't do anything here. And so the only thing you're left with is these parts of the q and q bar operators, but those have total derivatives in them. So that means that the only way you can get a supersymmetry variation for D is if it transforms into a total derivative. And indeed, what you find is that the way I've written it here, with lambda and rho being the components just below D in the superfield, for example, Q of D will basically transform into D slash of rho bar, and Q bar of D will be D slash of lambda. So Q of D and Q bar of D transform into total derivatives, and that's automatic because D sits at the very top of the superfield. It can only transform into derivatives of things below it. Okay, so that's great. That means that this thing, which I'll call ID, is a D-term Lagrangian. It's just the integral of the field D of x. This thing is actually supersymmetric because it satisfies our requirement that it transforms into a total this transforms into a total derivative under the Q and Q bar commutators, and then the integral makes it invariant. Okay, so let's try to see how this works in superspace. After all, we introduced superspace to make all this easier. In superspace, the way you pick out the D component of a superfield is by doing an integral. Okay? So remember that if you do Grassmann integrals, they effectively pick out coefficients of Taylor expansions. And we have such a Taylor expansion here, so if we do a Grassmann integral over all four theta and theta bar coordinates, we're going to pick out exactly D. So we can simply write this D term as a d for theta integral over the entire superfield. Where by d for theta here, I really mean d theta 1, d theta 2, d theta bar 1 dot, d theta bar 2 dot. It's really a volume integral over the odd directions of superspace. Okay, so now let's instead use this formula to check very easily that this D-term Lagrangian is indeed supersymmetric. If you want to compute its variation, its SUSY variation, you just act with the variation under the integral sign. And then you use this rule, which is that the SUSY variation is given by the action of the boldface Q and boldface Q bar differential operators acting on S. Now, I'm not going to write that out again, except schematically. So if you look over there on the very left, the formulas for Q tell you that Q involves a dd theta differential operator and also some other differential operator that involves a space-time derivative. Okay, this is the Q part. And then there's a similar Q bar part, which I'll not write out explicitly. So the space-time derivative we've already encountered, and that thing is just going to be killed by the ordinary space-time integral out here. So that thing drops out once you do that integral. And we're left with a term that is just a superspace derivative, a dd theta derivative. But that drops out when you integrate over d4 theta, right? Because remember, what's the rule? d4 theta picks out the theta squared, theta bar squared component of a superfield, right? But if you first act on a superfield with dd theta, then you will necessarily remove one theta from every term. And so there won't be a theta squared, theta bar squared term in that superfield after you do that derivative, and then this thing evaluates to 0. So you can think of that as translational invariance in the odd directions of superspace. So that also goes away, and that means that this whole thing is invariant. So this is a very easy way of seeing that D terms give rise to supersymmetric Lagrangians. So we managed to produce an example of a supersymmetric Lagrangian, and the question is this useful for anything? And the answer is not yet, really. I mean, it depends on what you're doing. We would like to write down an example of a standard Lagrangian for conventional fields like scalars and fermions and so forth. And we haven't succeeded in doing that yet. D should be some composite operator made out of these fields, and we haven't even seen how to construct these fields yet. However, if you are studying an abstract conformal field theory, where you don't necessarily have elementary fields and you just have a list of all the operators, then this makes perfect sense. If you happen to have a long multiplet, long superfield, of some scaling dimension, then you can abstractly ask what is the list of all D-term Lagrangians that you might be able to add to this theory, and you will be able to write such a term for every long operator, every long multiplet in the theory. So that can be useful for analyzing the RG flow in and out of strongly interacting conformal fixed points. Okay. So in order to write down simple Lagrangians, we're going to have to go beyond the long multiplet that we've been working with so far. Right? We've just been working with a general superfield. Instead, what we have to do is look at constrained superfields. Superfields with fewer components than this field. So what do I mean by constrained superfields? Well, for example, you can start imposing conditions on S as long as they are compatible with the action of supersymmetry, as long as they are compatible with the SUSY algebra and the action of the Qs and Q bars. So a simple example of that would be a reality constraint. You could demand, for example, that S is real. That's a perfectly supersymmetric constraint, then it would cut down the number of component fields by half. For example, C would have to be real, and rho bar would have to be the complex conjugate of lambda, and so forth. So that's an example of a good supersymmetric constraint. And that's also an interesting constraint to study, but the class of Lagrangians we'll study today will not make use of such a real superfield. Instead, we're going to explore a different constraint. And we're going to make use of this fact here, namely that covariant derivatives of superfields are, again, superfields. And what does that mean? It means that d alpha of s and d bar alpha of s itself is a closed, sensible, and consistent representation of supersymmetry. And it's perfectly sensible and consistent with supersymmetry to set that representation to 0. Okay? So one way of obtaining constraints on superfields is to take various combinations of covariant derivatives and set those to 0. Because the covariant derivatives themselves transform nicely under supersymmetry, or alternatively, if you want, because the d's commute with the q's, that's a supersymmetric constraint. So the constraint we're going to look at is the following one. Imagine you have a superfield which I'll now call phi that satisfies the constraint that d alpha bar of phi is 0. This is a complex superfield that satisfies d alpha bar of phi is 0. And we call such a phi a chiral superfield for reasons that will be somewhat clear. But one thing that is already clear, kind of the level of the notation, is that you should be reminded by this equation of various kind of d bar equations that you might know from complex analysis. So you can compare this equation, for example, with the equation d bar of f is 0 if f is a holomorphic function. And we'll see that that analogy is pretty good. So let's explore this constraint a little bit. By the way, before I go into the details here, I should say that if phi is a chiral multiplet, then you can consider taking the complex conjugate of phi and also taking the complex conjugate of this equation. So the complex conjugate of phi is phi dagger, or I'll also just denote it as phi bar. And then if you take the complex conjugate of this equation, the d bar gets turned into a d. So the complex conjugate superfield satisfies d alpha of phi bar is 0, and that thing is called an anti-chiral multiplet. And you see that in Lorentzian signature, there's no way to have a chiral multiplet without also having an anti-chiral multiplet, because they're just related by complex conjugation. And as we'll see in a little bit, that's very much related to the fact that CPT relates massless particles of different helicities, which played a role when we discussed the representation theory of the SUSY algebra a little while ago. Yeah.
So generally for holomorphic functions, you have the f to be not a function of z bar, for example?
That's right.
Yeah, so for the case of chiral superfield, is it also true, since we are writing it to be the covariant derivative with respect to alpha dot, I mean d bar alpha dot phi equal to 0, so is it true that it is also not a function of theta bar?
In some very precise sense that I'll explain next, but it's not true that it's a function of x and theta. It will turn out that you can make a change of variables, which I'll explain in just a second, and then you get to drop theta bar.
Okay, and this Fermi, another question I had, like when you took the derivative,
Can you speak up a little bit? I can't hear you, despite the microphone.
So yeah, so another question I had, when you have this Q alpha acting on D, for example,
yes.
Generally they are expanded like D is just explicitly a function of the bosonic coordinates.
Well, D is a field. D is a local operator.
Right, like is D x theta bar, or just D of x? I mean, is it a function of just the bosonic coordinates or also the fermionic coordinates?
Sorry, which D? There are a lot of Ds on the board.
The capital D.
This one?
No. Lower. The last line.
This?
On your left.
Okay.
On just within the commutator. Yeah, that one.
This?
These Ds. Yeah.
These Ds are these Ds.
Yeah, just a function of x's, right?
Yeah. Sorry, I'm always trying to write D of x to emphasize that it's just the.
Yeah. So
the
these
D term.
Q alphas essentially act on the theta square, theta bar square also, because there is a dd theta, the q alpha.
So be careful. So these Qs, these are ordinary Qs, not boldface Qs. These are operators. These are the operators that make up the supersymmetry algebra. They are not these differential operators.
Okay. Oh, okay.
So the whole point of this exercise is that commutators, which I've erased, I guess, commutators of things with the supercharges, which are operators on Hilbert space, are represented on superfields by the differential operators, boldface Q.
Okay, thank you.
Yeah. Okay. Good. So one way to attack this constraint, this chirality constraint, is just to start with the component expansion of the general superfield here in complete generality, and just compute d bar alpha of it explicitly using this formula, and just solve. This is a fun exercise, and I encourage you to do it if you haven't done this before. It's a little bit of spinor algebra. But there is a kind of a shortcut, which is roughly implementing what you suggested, which involves dropping one of the superspace coordinates. So let me explain how that works. So one thing that is completely clear is that the d bar operator over there, the supercovariant derivative d bar, annihilates the theta coordinate. That's because d bar contains derivatives with respect to either theta bar or spacetime, and therefore it annihilates theta. That's easy. So a chiral superfield can definitely be a function of theta. However, the thing with the spacetime coordinates is a little bit more complicated because d bar alpha of x is not 0. Okay? So what we have to do is shift x by something involving the thetas to make it 0. So what we're going to do is introduce a new coordinate, sometimes called the chiral coordinate, y, which is x. Let me see, the plus. I think it's plus I theta sigma theta bar. And then it's easy to check that d bar annihilates y, because the piece where the spacetime derivative in d bar hits dx exactly cancels the piece where the dd theta bar derivative hits the theta bar over here. So the only thing you have to be careful about is some minus sign as you bring the dd bar through the theta. And then you'll get this vanishing condition. So d bar annihilates theta, d bar annihilates y, and of course d bar does not annihilate theta bar. And therefore, we learn from this that a chiral superfield can be an arbitrary function of theta or y, but it cannot depend on theta bar. So your intuition that one of the coordinates should drop out is correct after we do this shift. So now we just have a function of y and theta. And in order to go from this expression to component fields, we do exactly what we did for the long multiplet, which is to realize that we have one Grassmann odd coordinate left, which is theta, before we had 2. And we're just going to expand in a power series in theta. And the coefficients are going to be functions of the bosonic coordinate y. So the bottom component will be some bosonic field, which I'll call phi without the, little phi without the crossbars, phi of y. And then there'll be a theta component, which will multiply some fermion, psi of y. And for conventional reasons, I'll put a factor of root 2 here. That'll make our Lagrangians that we'll write in a little bit more civilized. And then there's a theta squared component, which I'll write as with coefficient f of y. And because we only have one theta, one spinor theta, so two theta components, the Taylor series in theta stops here. Okay. So this is good. We have here a much smaller number of components, and we have a scalar and a fermion, which look like nice ingredients for a Lagrangian. We also have some field F, which we don't quite know what to do with yet. And if we want to go from this formulation back to the formulation in terms of the space-time coordinates x, right? Ultimately, we would like to express all the fields as functions of x, not of this shifted y. Well, that's easy to do because you just undo the shift. You just plug in y is x plus I theta sigma theta bar, and then you Taylor expand that. Right? For example, phi of y is phi of x plus I theta sigma theta bar d mu x. That's the first term in the Taylor expansion. And then there's a second order term, which is I squared over 2. There'll be 2 copies of this theta theta bar term and a double derivative of phi evaluated at x. And then the Taylor series stops because here we have 2 thetas and 2 theta bars. So you see you can do this and re-expand the entire field back in terms of position space. This can be cleaned up a little bit, by the way, using some spinor identities. It's also a nice exercise to do. Some spinor identities and the fact that the thetas are anti-commuting. So you can convince yourself as an exercise that this term is completely identical to 1/4 theta squared, theta bar squared, box of phi, where I'll always use box to denote the massless wave operator. Okay, very good. And you can do exactly the same thing with y. And if you do that, you'll also get a term with 1 derivative on y. And for f, nothing happens because we already have 2 thetas here. So when we expand, all the terms with theta, theta bar vanish. So actually, we can replace this by x for free. And that's it. Yeah, maybe I'll just write down what happens to psi as well, since we'll need that. Well, I'd rather not, actually. Very good. So here we have even better ingredients to make a Lagrangian. For example, we have not just the field phi, but also an important component in what we hope to be its equations of motion. And similarly, when you expand psi, you get derivatives of psi, which you again need for its equations of motion. Okay. So before I start writing down Lagrangians using phi, let me make a quick detour, because the fact that we introduced the Chiral Superfield will allow us to introduce a second kind of supersymmetric Lagrangian. You see that in some moral sense, this operator f of x is the top component of the Chiral superfield. That's not really true, because when you expand back in x space, there are theta squared and theta bar squared components, but they all involve derivatives of the other operators. So there's a theta squared, theta bar squared component, which is kind of like a d term that involves the box of phi. There's also some theta squared, theta bar operator that involves the derivative of fermion. But f is the highest operator that's not a derivative of something. Okay? And following the same logic that we used over here to write d-term Lagrangians, that means that we can use the operator f to construct another type of supersymmetric Lagrangian, which is usually called an f-term. Okay? So let me write that right below the d-term. An f-term is simply the d4x integral of f of x. And by the same component logic as before, it's very easy to convince yourself that the supersymmetry variation of f is a total derivative of all the other fields. So this thing is also supersymmetric. But just to practice a little bit with superspace, let's again see how this comes about in superspace. So f of x is the theta squared component of the superfield big phi. And just like we picked out the theta squared, theta bar squared component by integrating over all of superspace, you can pick out the theta squared component by only integrating over the chiral half of superspace that involves the thetas. So you can write that as d2 theta times phi. So now we have a, sorry, this is the F term, Lagrangian. So now you have a d4x integral and the d2 theta integral of the chiral field phi. So how do you see that that thing is supersymmetric in superspace directly? Well, again, you can act on it with the SUSY variation, which, remember, just involves essentially acting with either the differential operator boldface Q on phi or the differential operator boldface Q bar. Okay, so let's look at the Q bar term first. Here we use a nice fact, which is that you see from this formula over here that the Q bar operator only differs from the D bar operator by this sign here in the second term. And the second term explicitly involves an ordinary spacetime derivative. So that means that as long as you allow yourself to drop ordinary spacetime derivatives, you can replace Q bar by D bar. Okay? But of course, since we are under a d4th x integral, all total derivatives drop out. So indeed, we are free to replace Q bar by D bar. So this, up to total derivatives, is proportional to D bar alpha of phi, but phi is chiral. So by definition, D bar alpha of phi vanishes. Okay? So that's half of the supersymmetry is done. And the other half is easy. The other half works exactly like for the D term. Here there's no trick involving D bar anymore, but just again, remember that Q, boldface Q involves both a dd alpha and a spacetime derivative. And again, spacetime derivatives drop out because of this integral. But now we have an explicit d2 theta integral. And that d2 theta integral also kills this dd theta term. So we can still use translational invariance along the theta directions to get rid of this term. We couldn't do that over here, right? If you look at Q bar, it contains not dd theta, but dd theta bar, right? And we're not integrating over dd theta bar. So this argument wouldn't have worked here. It only works because phi happens to be chiral. So that's the reason we can get away with only integrating over half of superspace and still getting a supersymmetric result. Okay, so now we have D terms and F terms, and that's more than we'll need to study some nice examples. So the first thing we would like to do is to write some kinetic terms for the scalar phi and the fermion psi. So a kinetic term should better be bilinear in the fields, and it should involve both phi and its complex conjugate. Right? The kinetic term for a massless scalar like phi looks like something like d mu phi bar, etc. And the kinetic term for psi would involve psi bar, some sigma matrix, and d mu psi. So we need it to be bilinear, and we need it to involve both phi and phi bar. Now, the chiral superfield, big phi, does not involve phi bar, right? It only involves phi. That's the whole point. It's holomorphic. So in order to get a phi bar, we're also going to have to look at the anti-chiral superfield phi bar, or phi dagger, and then we're going to have to take a bilinear in those. So very natural guess is to just look at phi dagger phi. Phi dagger phi is some nice superfield, and it's easy to see that phi dagger phi is not a chiral superfield, right? Because it involves one holomorphic object and one anti-holomorphic object. Phi is chiral, phi bar is anti-chiral, but their product is neither. And that means that we should not use the F term Lagrangian here. We should use the D term Lagrangian. We should try to construct a supersymmetric D term based on the long superfield phi dagger phi. So let's do that. So we'll define the superfield S to be phi dagger phi, or equivalently phi bar phi. And then we'll write a D-term Lagrangian, which is exactly the same form as we had over there. So we have a full integral over superspace of this phi dagger phi. All right? And in order to evaluate this thing, what we're going to have to do is to look at the product superfield phi dagger phi. Right? So we need to actually do this multiplication out in components and then pick out the theta squared, theta bar squared component. So that's also a fun exercise, which I'll not do in detail. It's relatively straightforward because we have already written what phi is. So now you just need to take the complex conjugate and multiply out and keep all the terms that involve 4 thetas. And after you do that, you will find the following expression. There's an f bar f. There are some terms involving phi bar and box of phi. And there's a term involving box of phi bar times phi. Then there's some mixed terms involving d phi bar and d phi. And then there are similar terms involving fermions. So there's a term involving a derivative of psi bar. And then there's a term involving psi and the derivative of, psi bar and a derivative of psi. So even though I'm not going to do this out, you can schematically see where these terms come from. The f of bar term is very easy, right? Because we have a theta squared times f from phi, and we have a similar theta bar squared times f bar from phi bar. The various terms with phi are also easy. For example, remember that there's a theta to the 4th term here with a box phi. So that already has 4 thetas, and it just picks up the lonely phi bar from the anti-Chiral superfield. So that explains this term. And this term is just the same thing, but in the other order. The mixed term with 2 derivatives on each of the phi's comes from picking this intermediate term from the chiral superfield and the analogous term from the anti-chiral superfield, and so forth. So it's pretty straightforward. And of course, these terms can be further simplified by integrating by parts. So let me write this out. We can consolidate all the terms with phi's and all the terms with fermions into the following very simple looking Lagrangian. There's an f bar f. There's a d mu phi bar, d mu phi. And then there's a minus I psi bar, d mu psi. That's it. And we don't have to worry at this point whether or not this thing is supersymmetric, because this whole machinery guarantees that it is so. If you would like to check it, then you have to explicitly take the commutator of this component expression and make sure that it goes into a total derivative. That's already a little bit of work. So you see here that phi is a nice massless free complex scalar, standard kinetic term. The fermion psi is also a standard free Weyl fermion. And then we have this gadget f, which doesn't seem to do very much. It doesn't have a kinetic term, doesn't have any derivatives in its Lagrangian, and therefore it's not a propagating field. It doesn't have any dynamics. And it's completely correct, even in the quantum theory, to integrate it out using its equations of motion. Right? The path integral over f is just a Gaussian integral. There are no derivatives. F doesn't couple to anything, so you can just integrate it out by going to the saddle point. And here the saddle point is completely trivial. because the equations of motion just set F and F bar to 0. So the actual dynamical theory, or what's usually called the on-shell theory, just has phi and psi, and F is what's called an auxiliary field. And its role in life is to make sure that superspace works the way we said it does. Namely that supersymmetry transformations are implemented in a consistent way, even long before we ever talked about which Lagrangians we're going to discuss and what the dynamics is, right? We were able to discuss superfields even without specifying the dynamics of the theory, and F is important in order to get that to work out right. Right, and the other comment I wanted to make is that you see here explicitly realized in a very clear way the massless particle content of n equals to 1 supersymmetry that we derived using representation theory a little while ago. We said that the representation theory of the n equals 1 superalgebra led to massless particle multiplets of helicity 0 paired with a helicity 1/2 state, and then by CPT, a helicity minus a half state paired with another helicity 0 state. So you have two helicity 0 states, and those are the two complex scalars described by phi. And then we have a left-handed fermion state and a right-handed fermion state, and those are described by the Weil spinor psi alpha and its complex conjugate. So this is the field analog of the massless particle multiplet we had before. And by the way, just as an aside, the fact that the massless particle multiplets were annihilated by half of the Qs, remember the massless particle multiplets were always half BPS, it has a mirror in the field description as well. It's mirrored in the fact that phi is a constrained superfield. It's a chiral superfield, which has, roughly speaking, half as many degrees of freedom or component fields as a general unconstrained superfield. So that's also sort of a nice analogy. Okay, so far we have produced a free supersymmetric theory for the second time in this set of lectures. And now we would like to add some interactions. And in order to do that, we're going to make use of the F-term supersymmetric Lagrangian that we explained over here. Okay? So the F-term Lagrangian is something you get when you integrate any chiral superfield over half of superspace. Now, putting just phi here is not particularly interesting. Because if you just put phi here, then you're going to just put the auxiliary field F there, and that still doesn't do anything particularly remarkable. If you're an aficionado, you can say that it shifts the vacuum energy, but that's a little bit semantic. And so instead, what we'd like to put here is a more interesting chiral superfield. And we can make more interesting chiral superfields than phi by remembering that, first of all, products of superfields are superfields. But secondly, it's very easy to see that products of chiral superfields are still chiral, right? If something is annihilated by d bar, then any power of it and any product of it with another chiral superfield will also be annihilated by d bar. So that means that we can produce a more interesting example of a chiral superfield by considering things like phi squared, phi cubed, etc. Or if you wish, I mean, if you just sum these things up with some random coefficients, you'll get an arbitrary holomorphic function of phi. This thing is holomorphic. And because of that, it'll satisfy this condition that d bar annihilates it. If you want to be extremely pedantic, you could do that computation explicitly using the chain rule. Then you get w prime of phi, and there's a d phi, and that's 0. Okay, so this thing here is called the superpotential, for reasons that will come clear in a second. And it's completely standard to denote it by w. And now we're going to shove this w chiral superfield into our F-term Lagrangian over here. Okay? So we have a chiral superspace integral d2 theta w of phi. We said before that that thing was supersymmetric. I should say at this point that by itself, this is not an acceptable Lagrangian because it's holomorphic. It's always complex. So if you want a Lagrangian that's sensible and real, you have to add to this thing its complex conjugate. So if you add its complex conjugate, that thing will involve a d2 theta bar integral w bar, which will be an anti-chiral superfield, and it'll be supersymmetric for very similar reasons. Okay, but just in order to keep the writing down, I'm going to focus on this chiral half. Good. So just as we did for the kinetic term, we're going to have to expand this thing in components, right? We're going to have to expand this thing in components. And actually, in this case, it's even easier than before because the whole thing is chiral. So we might as well change variables from x to y and just use this component expansion. We don't have to worry about all the derivative terms we had before. So we have to pick out theta squared pieces, and there are only two ways to make a theta squared here. You can either take 1f and pair it with a bunch of phi's, or you can take 2 psi's. Okay? And what that translates into when you evaluate this in components is the fact that you'll get a term that looks like w prime of the superpotential times f. It's roughly doing a first order Taylor expansion and then picking the f term of the one field that sits outside, or terms with 2 fermions, psi alpha, times the second derivative of w. So this is the f term. And now we can add that thing and its complex conjugate to our supersymmetric Lagrangian over here. So we have ID plus IF plus IF bar on the left-hand side. This was the D term, and now we're going to add to it the F term. And the complex conjugate of the F term. Okay? And now you see very clearly that we have produced an interacting theory, right? If W is not too trivial. For example, here we'll get some sort of Yukawa couplings between the scalars phi and the fermions. And we've also introduced some interactions that couple the scalars to this auxiliary field F. But it's still true that F doesn't show up with any derivatives. So just as before, it's completely legitimate to integrate it out using its equations of motion. Just compute the variation and go to the saddle point. And so if you do that, then for example, the F bar equation of motion will tell you that F from here plus W prime bar from this term is 0. So that means that F is minus W bar, W prime bar. So you can solve for F in terms of the scalars, and when you plug back in for F and also for F bar into the Lagrangian, you see you're going to get something that's bilinear in the F's, and therefore it's going to be quadratic in this expression. So that thing is going to produce for you a purely scalar term in the Lagrangian. It's going to be a scalar potential, which only depends on phi and phi bar, and that is going to be the absolute value of W prime quantity squared. Okay? So the actual genuine scalar potential of the theory is determined in terms of this bilinear quantity that involves the superpotential. And what you see from the very definition, because it's an absolute value squared, is that this scalar potential is totally positive. It's positive definite, or 0. And of course, the lowest energy points are exactly at 0 energy. If if you have a positive potential, then the minima are going to be all at 0. So the vacua have 0 energy and are determined by the equation W prime of phi is 0, which is a nice holomorphic equation. So even though the whole potential isn't holomorphic, finding the vacua involves just solving some holomorphic equations. And moreover, the vacua have exactly 0 energy. That's actually something that follows in complete generality from the supersymmetry algebra. You can convince yourself using just the QQ bar anti-commutator, which involves the Hamiltonian here on the right-hand side, the P0 term, that QQ bar is a positive definite or a positive semi-definite operator. And so, if the energy is 0, then Q and Q bar annihilate the state that you're considering, and that's a supersymmetric vacuum. Conversely, if you have a state that's annihilated by all the supersymmetries, it necessarily has 0 energy. So that's an if and only if statement. Okay, so let me study in the last part of this lecture the quintessential example of such a model. This was basically the first interesting interacting supersymmetric model studied in detail in 4 dimensions. And that's the Wezumino model. So that's the model you get when you restrict the superpotential in such a way that the resulting Lagrangian is renormalizable. And you get a renormalizable theory if W is at most cubic. So we're going to have here a quadratic term in phi with some coefficient m, and a cubic term in phi with some coefficient g. These are coupling constants. There's no linear term because we can shift that away using some Fielder definition. So this is the most general renormalizable superpotential for a single phi. And using this prescription here to find the minima, right, we have to just set W prime to 0. So W prime is this thing, and it has 2 zeros, one at phi equals 0, and one at phi equals what? Minus 2m over 3g. So you see there are 2 nice supersymmetric 0 energy vacua. Which are incidentally exactly degenerate, because they've both got 0 energy. And if you take this W and you plug it back here, right, you see that the scalar potential is going to have an m squared phi squared term, which is going to give phi a mass, m. And there's also going to be cubic and quartic couplings. And the terms involving the fermions are going to give you nice renormalizable Yukawa couplings between phi and psi. Good. So far our discussion of the model has been entirely classical. We've just written down Lagrangians, and what we did here very quickly using this nice fact is to find the classical vacua, and we found that there are 2 supersymmetric, exactly degenerate classical vacua. And of course, if you are a non-supersymmetric person, then this conclusion wouldn't necessarily hold up quantum mechanically. The structure of the vacua could change when you include quantum corrections. The degeneracy could be lifted. A new vacuum might appear. Who knows? All sorts of things could happen. You'd have to start analyzing this model quantum mechanically and doing perturbation theory in the coupling G. And the thing I want to explain to you in the last 20 minutes is the sort of absolutely remarkable property of supersymmetric theories of this kind, things that involve holomorphic quantities like the superpotential, which is that they obey what's called non-renormalization theorems. And non-renormalization theorems in this context are the statement that the superpotential W, the holomorphic superpotential W, does not receive quantum corrections, even when you start computing corrections in G. Okay, so if you look at the full quantum superpotential, the full effective superpotential of the quantum mechanical theory, let me call it W quantum, you actually find that it is exactly equal to W, which is the classical or tree-level superpotential. So that's a very remarkable fact, a highly non-trivial fact that relies on all sorts of cancellations that are built into Lagrangians like this one. And it means in particular that any analysis of the vacua you do using this equation applied to the classical superpotential is correct in the quantum theory. So in fact, the fact that we found two exactly degenerate supersymmetric vacua here will persist unaltered in the full quantum theory. By the way, I should say that this does not mean that the entire theory isn't renormalized, right? Remember that it was important that we had both F terms and D terms in this Lagrangian. The kinetic term was a D term, and the superpotential term was an F term. And the difference between them is that the F term is holomorphic, and it's half BPS, and it's protected in some sense by supersymmetry, whereas the D term is not. So for example, once you start computing quantum corrections, the D term will actually be renormalized. You'll have wave function renormalization factors here, for example, in perturbation theory. That will change the D term. So it doesn't mean that the theory is trivial or rigid. It also doesn't mean that it's necessarily exactly solvable in any sense. But there's some sector of it, namely this holomorphic sector described by W, and the vacua and things like that, that are protected enough to be analyzable in the full quantum theory. And I'm only going to explain this in the context of the simple Wezumino model, but the real power of these theorems comes when you start analyzing supersymmetric gauge theories and strongly coupled theories, and these non-normalization theorems and their friends give you basically the ability to determine the exact quantum mechanical space of vacua of strongly interacting SUSY gauge theories. Sorry?
Lagrangians involving just the chiral multiplet or the vector multiplet?
Well, this statement that I've written here, that W is completely unmodified, is only true in simple Lagrangians for chiral multiplets.
No, I'm just talking about the theory.
In theories with gauge fields, there can be new terms that are generated non-perturbatively, but they are extremely constrained. They're very, very restricted. So in many cases, you can still determine them exactly. So the same logic that we'll explain that gives this for chiral multiplets allows you to exactly compute what the corrections are, even in cases which are much more complicated. And this observation, which is mainly due to Seiberg, is basically what led to the enormous progress in analyzing strongly coupled SUSY theories in the early 90s. And in fact, I mean, it's possible to prove this non-renormalization theorem using Feynman diagrams, using supersymmetric Feynman diagrams, so-called supergraphs. But I'm going to tell you the argument that Seiberg gave based on symmetries, which is the one that also generalizes. Okay. So we would like to analyze this quantum superpotential. And let me say one or two words about what I mean by that. You might be familiar with different notions of effective quantum superpotential. There's the Wilsonian effective superpotential, which you get by integrating out massive fields down to a small but finite energy. There's the notion of a 1pi effective action, which you get by basically integrating out almost everything. These things are slightly different, and one of them is not always defined, and there are a bunch of subtleties to worry about. But the good news is that in this model, these subtleties won't actually bother us because the model is massive, and therefore it turns out that these different notions actually coincide. So this WQ here is and you can think of it either as the Wilsonian or the 1pi effective superpotential. And instead of actually trying to integrate out modes, order by order in perturbation theory, we just imagine that we somehow do that and then write down an ansatz for what the resulting W quantum is based only on general principles like symmetry, locality, and the constraints that we've already learned about. So that's, for example, exactly the same logic that Mukund used in his lectures to constrain hydrodynamics. And basically the only thing we have available to constrain W quantum, in addition to locality, are symmetries. So we already learned, for example, that any W that is worth the name should be a holomorphic function of the chiral superfield phi. Okay, so we definitely need to insist that this W quantum, this I do not want to erase, sorry. Maybe I'll erase this. So we definitely want to insist that W quantum is a holomorphic function of phi. Okay, that's good. That follows from supersymmetry, so that's already non-trivial. And other than that, well, what do we have? I mean, what other symmetries does the model have other than supersymmetry? And the answer is not that many, right? If you just think of M and G as coupling constants and you try to analyze what are the symmetries of this Lagrangian, you'll see that that really doesn't have many interesting symmetries beyond supersymmetry. So we've implemented supersymmetry at the level of demanding that W quantum is a holomorphic function of phi, and then we're kind of stuck again. The really crucial insight is that it is possible to view the coupling constants M and G, which are just numbers in the Lagrangian, as expectation values, or VEVs if you wish, of chiral superfields. So you somehow imagine, as explicitly or implicitly as you would like, that there are some other chiral superfields in the theory, and the best way to imagine them is really as kind of static, non-dynamical superfields, which are just sources or backgrounds that you get to specify. But if that's not palatable to you, you could also imagine that they're somehow extremely heavy and don't fluctuate very much, but are basically dynamical. Either way, you imagine that M and G are not just numbers, but that they're actually expectation values of bottom components of some chiral superfields. Let's call them script M, and well, it's kind of supposed to be script G. Okay? And when you say that, you don't just imagine that M is a number, you imagine that M is a full superfield with exactly the same component structure that we wrote for phi before. And that's consistent because, you see, the way that M and G appear here in the Lagrangian, right, just as single holomorphic numbers, makes it possible to upgrade this M to a chiral superfield without violating the requirement that the superpotential should be holomorphic in all the chiral superfields. So we can replace this M by script M and this G by script G, and both M and G are themselves chiral superfields, and if you want to be very precise, you should think of them as background chiral superfields. So non-fluctuating, rigid objects that you just put into the theory as sources. Now, depending on your experience and point of view, you either find this extremely trivial or extremely strange, but if you accept it, then you immediately get a very powerful handle on the theory. Because in addition to demanding that the superpotential should be holomorphic in the dynamical fields phi, you now also get to demand that it be holomorphic in the background chiral superfields script M and script G. You see, before I sort of left the M and G dependence in here implicit, and I definitely didn't commit to whether it should be holomorphic or not. But now that I know that script M and script G are chiral superfields, I really need to demand that this W quantum is holomorphic in all of them. Okay, so that's the first step in proving the non-renormalization theorem. The second step is realizing that once you view M and G as fields, not just as numbers, the symmetry, the symmetry of the theory enhances to what are called spurious symmetries. So spurious symmetries are things that are not symmetries of the actual theory, when M and G are just numbers, but that look like symmetries when you view M and G as background fields. So in other words, they're symmetries that are broken by the parameters M and G, and you can compensate the breaking by assigning transformation rules to these parameters. So what symmetries does this problem have? Well, for example, we could contemplate a U1 flavor symmetry that rotates the superfield phi and its bottom component with charge 1. Okay, so this term would have charge 2, and this term would have charge 3, and the superpotential I claim overall should have charge 0. So the flavor charge of the superpotential better be 0. And that I cannot achieve if I just view M and G as numbers, but I can achieve it if I assign them charge -2 and charge -3 under this symmetry. Let me make a small comment about why I assigned flavor charge 0 to the superpotential. There's various ways of seeing it, but recall that the F term, right, Lagrangian, was proportional to d2 theta w phi. And theta is the superspace coordinate. Superspace coordinate that also appears, for example, in the Q and Q bar differential operators that represent supersymmetries. Now, the supersymmetries should be neutral under a flavor symmetry. Remember, in the beginning of these lectures, we made a distinction between flavor symmetries and R symmetries, and the distinction was that R symmetries don't have to commute with the supercharges, but flavor symmetries do have to commute with them. Yes, please.
Full chiral superfield. Is that small phi or a big phi?
I think in this formula, I'd rather think of it as big phi. Yeah. Here I actually meant small phi, because I was evaluating the vev of phi, and only the scalar field in the bottom component had a vev. But yeah, up here, it's better to write big phi. Thank you. Okay, so if the Q's are neutral under a flavor symmetry, then theta must similarly be neutral under a flavor symmetry. Let me also write an entry in this table for theta. So the theta coordinate, superspace coordinate, has to be neutral under flavor symmetry. And if theta is neutral, then the only way that the whole F term can be neutral is that W is also neutral. Okay. So we managed to cook up a spurious U1 flavor symmetry. It's called a spurious symmetry because it's not really a symmetry of the theory. It's only a symmetry after you do this monkey business with the background fields. And for this reason, the background fields M and G are sometimes called spurions, to remind you that they transform under some spurious symmetry. Okay, so that's one symmetry we can talk about. But remember, we discussed two kinds of global symmetries. We discussed flavor symmetries and we discussed R symmetries. So we can also see if this model has potentially a U1R symmetry. What's the difference? Well, the difference is that the U1R symmetry gets to rotate the supercharges. Okay? First of all, I don't know if you remember this, but in general we said that n extended supersymmetry in 4 dimensions can have at most a UN R symmetry. So since we're doing n equals 1, U1 is the most we're going to get. The supercharges have to transform by some phase under this U1 necessarily. And the supercharges involve theta and theta bar. There's a theta in the denominator and a theta bar in the numerator. So if we assign, for example, charge, let's see, what did I do? Let's say charge -1 to theta, then this whole object here will have charge +1, and theta bar will also have charge +1, R charge +1, so that means that Q has R charge +1. So the real difference here between a flavor symmetry and an R symmetry is that the superspace coordinate carries R charge -1. And then by the same logic that before said that the W superpotential should be neutral under the flavor symmetry, says now that it should have R charge 2, because we have two thetas of R charge -1 sitting in front here. Okay? So W has R charge 2, and this has R charge -2. Very good. So now let's try to make a U1 symmetry acting on phi that gives W R charge 2. Well, that's very easy. We can again give phi R charge 1. So these formulas for how the phi pieces transform are the same, but now we don't want to make W neutral. We want to make it have charge 2. So that I can achieve by giving M 0 R charge and G R charge 1. Sorry, -1. I think 1 second. Right. Okay, so we have produced two U1 symmetries, and we have a holomorphic function of phi, M, and G. So now we just have to impose that W quantum is also invariant under those symmetries. So how do we do this? Well, it's easy to make a completely invariant combination of phi, M, and G. Consider the following ratio. Consider the ratio psi, which is G phi divided by M. So G, let's see how this works. So let's for example compute the U1 flavor charge. So phi has flavor charge 1. G has flavor charge -3. And M has flavor charge -2, but it sits in the denominator. So you see that this thing is actually flavor neutral. Okay, so it has 0 flavor charge. And we can also check the R charge. Phi has R charge 1. M has R charge 0. And G, we said, has R charge -1. So psi also has 0 R charge. So psi is completely neutral under these two U1 symmetries, and it's also holomorphic in G, phi, and M. So we can, first of all, consider adding to the superpotential or constructing the superpotential in terms of an arbitrary holomorphic function of this psi. Very good. Now, this doesn't quite work yet because the superpotential has to have R charge 2, and this gadget is completely neutral. So we need to multiply this with something of R charge 2 in order to get a good candidate superpotential. And there are many ways of doing this. I'm going to multiply it by the mass term, M phi squared, which is just this piece of the Lagrangian, which of course has R charge 2. Okay? So this ansatz here is the most general holomorphic ansatz in terms of M, G, and phi that also respects these spurious U1 symmetries. And of course, the original tree W, which is just M phi squared plus G phi cubed, corresponds to F having a very special and simple form, namely just 1 plus psi. The 1 term gives me the original mass term, and the psi term, remember psi is G phi over M, the M cancels out, and I get G phi cubed. So this is what the original tree level W looks like. So the content of the non-renormalization theorem is the statement that this function f, maybe I should write f tree here, or f classical. And here I'll write f quantum. The statement of the non-renormalization theorem is that the full quantum mechanical f is exactly equal to the tree level f. And that's what we have left to show. But now f is just a function of a single variable psi. Okay? So the problem has gotten simpler. Why has it gotten simpler? Because now we can go to weak coupling without changing psi. See, there's only one regime, one quantum regime that we actually know anything about, and that's the weak coupling regime, when G goes to 0. So we're going to take G to 0 in a way that keeps this ratio psi fixed, and then we're going to be able to say something about this function f. So there's basically not much more to it than what I just said, but let me just write a few things out. So we're going to take a weak coupling limit. G going to 0, and we would like to take this limit in such a way that, that psi stays fixed. So that means we're also going to take m to 0, and we're going to take the ratio G over m to be fixed, and phi doesn't do anything, just comes along for the ride. So G over m fixed implies psi fixed. So what this means is that there's a slice in the two-parameter space, G and M, that goes arbitrarily close, parametrically close to the weak coupling region, along which this function here doesn't change. Okay? If I want to evaluate what the functional form of f of psi is, I can do so at arbitrary weak coupling by taking this limit. And that is how we're going to get our result, because at weak coupling, of course, at parametrically weak coupling, there are no quantum corrections, and f is just equal to its classical tree-level value. Okay? So f quantum of psi is f classical. And this establishes the non-renormalization theorem for W. So let me recap the important ingredients in this argument. Holomorphy of the superpotential applied to both the dynamical fields and the background fields that you got by promoting coupling constants to spurions, to background fields. Gave you a constrained form of W. Symmetry analysis of both genuine and spurious global symmetries cut down the functional form even further. And then at the end, we had to go to some weak coupling region and match onto some result that we knew about. And that's the nature of the argument, even in more general contexts and even in interacting gauge theories and so forth. So these are the three salient ingredients that I wanted to emphasize to you. And the non-renormalization theorem is perhaps the single most important reason why we study supersymmetric quantum field theories. There are two large communities in physics that are interested in supersymmetry. There are people who are interested in particle physics beyond the standard model, and there are people who are interested in studying strongly coupled quantum field theories and non-perturbative phenomena and so forth. And both of them love supersymmetry, and they both love it for this reason. The non-renormalization theorem in particle physics is what allows you to explain or maintain in a natural way large hierarchies, okay? Because large hierarchies are naturally destroyed by quantum corrections, but if there are no quantum corrections, then they can be maintained. So that's why SUSY plays an important role, continues to play an important role in BSM particle physics. And of course, if you want to analyze in a rigorous way strongly coupled quantum field theories, the non-renormalization theorem is your friend because it allows you to derive exact results. So I hope this gives you a little bit of a taste for different aspects of supersymmetry. We've taken a big survey across different dimensions, and then we derived some classic results in 4D n equals to 1 theories. So I think if you are interested and you want to delve further into the subject, then you're well prepared to start reading some of the references that I gave at the beginning of the lectures, and I'll stop here. Thank you.
Does the non-renormalization theorem constrain or do anything else to building superconformal field theory?
Sorry?
Does the non-renormalization theorem do anything to building superconformal field theory?
Sure. It's basically the reason why we are able to write down so many examples of interesting superconformal field theory. For example, perhaps the most well-studied superconformal field theory is 4D n equals to 4 SUSY-Yang-Mills, which has an interesting marginal coupling, which is the marginal gauge coupling. The non-renormalization theorem is what guarantees that this gauge coupling has beta function exactly 0, right? So that for every value of tau, you have an interesting interacting superconformal field theory. In a non-supersymmetric theory, you would always expect that some higher order contribution to the beta function would make it run somewhere.
When you find R charge for a phi, you consider that R charge for Q alpha. I didn't see why.
Why I assigned this particular... Well, remember what an R symmetry was, by definition. An R symmetry was some flavor symmetry, some U1 symmetry in this case, that didn't commute with SUSY. So if it doesn't commute with SUSY, it has to assign some charge to it, which is not 0. And I might as well choose it to be R charge 1. That's just a nice choice.
And I have another question. When you introduce the auxiliary field F, does in action level does F possesses any gauge redundancy or symmetry?
No. So F was a perfectly fine field. It was an innocuous scalar field that just gets integrated over in the path integral. And you see it has a nice, well, okay. Actually, I was just going to say it has a nice Gaussian form. Actually, it doesn't have a nice Gaussian form in Lorentzian signature. It looks like it's a Gaussian of the wrong sign. So if you want to be very precise about how you integrate it, you should rotate the contour to make the path integral converge. But at the level of detail that we've been doing things, because it's a free Gaussian field, and you can just basically work at the saddle point and forget about it.
Thank you.
Yes, please.
Is the non-renormalization theorem is dimension independent?
No, not quite. The non-renormalization theorem depends crucially on having some kind of holomorphic gadget, like the superpotential. And not every supersymmetric theory in every dimension has such a holomorphic gadget. For example, if you go down to 3 dimensions and you study theories with n equals 2 supersymmetry, which are basically the theories you get by reducing these 4-dimensional n equals to 1 theories, they will again have a holomorphic W. But if you reduce the amount of supersymmetry by half and you study 3D n equals to 1, that's something that only has one real supercharge, then the analog of W will no longer be holomorphic. It'll be some real function. And then there is no non-renormalization theorem to speak of.